Looks like we're live. Hello everyone and welcome to yet another Azuzin session. Let's make a little bit of an announcement and officially start the stream. Hello everyone, welcome. So red circle as usual, live on Twitch. And what are we doing today on Twitch.television website? Today we are generating Cellular Automata based on pixel art images. Does it sound interesting? I think it sounds kind of interesting, so I'm gonna give the link to twitch.tv/Zoling where we're doing all of that. I'm gonna ping everyone who's interested in being pinged, and there we go, the stream has officially started. So today we continue the project that we started yesterday, which I decided to call Autocell, but the name doesn't really matter, right? So I'm gonna give the link in the chat. I'm gonna copy paste it in the chat, and for people who are watching on YouTube, potentially we'll see, the winner gets tea. I'm gonna put that in the description. So let's take a look at the project itself. So I already, by the way, deployed it. So there is a website, right? So since it's written in TypeScript, right, it's a web application. So this is how it looks like. Right, and believe it or not, this is a straight up game of life, Conway's game of life. Right, it's that straightforward, right? So this is what we spent 2 hours yesterday implementing, right? And you can see this is a glider, this is a Conway's game of life. So what's up with that? Why did we need to implement yet another Conway's game of life? We didn't really implement this thing in a conventional sort of way where we would have like a if condition, right? If the amount of like alive neighbors is between 2 and 3 become alive and blah blah blah. No, we didn't implement it like that. We implemented this entire thing as a transition table, right? So let's take a look. So Autocell, I'm gonna go into the index.ts, and this is the implementation of the Conway's game of life, right? So this entire thing, right, it's a transition table, right? And the actual application is basically an interpreter of this transition table. So idea is the following, right? You have two states, dead and alive. We denote them 0 and 1 correspondingly. So essentially each state can be used as an index within this array. So we have an array of two elements, 0 and 1. So if you are currently dead, right? So if the current value is dead, you will get this table. If you are alive, you will get this table. Right, so by doing this kind of thing, you picked a table, the current table, and then you have another, you have two-dimensional thing, right? So now we have a two-dimensional table. So the first dimension denote how many dead neighbors you have, right? So by determining the amount of dead neighbors, you're picking the row within this table, right? So here you would put the amount of dead neighbors for that specific cell, and with the column you would pick the amount of alive neighbors of your cell, right? And thus you compute the next state of your cell, right? You see, it's a simple lookup table, and the dimensionality of this entire thing is gonna depend on the amount of states, right? So since in Conway's game of life we have only 2 states, this is a two-dimensional table. In a 3-state situation, you're gonna have 3 dimensions, and so on and so forth. And the entire thing is just like, you know, taking this entire table without even thinking what's in the table, and just like interpreting it, right? Just like taking the current state of the cell, then counting the amount of neighbors of different states, and just plugging all of that as an indices into this table and getting the next state. So why did we need to actually implement this Conway's game of life in such a weird way? Because we abstracted away from a specific cellular automaton, right? Now, one of the things we can do, we can, for example, procedurally generate them, right? And maybe try to find some interesting cellular automata, right? Or furthermore, we can take pixel art images, right? So I already like downloaded some pixel art images from the Open Game Art, something like this. They're actually kind of small, but I wonder if I can actually make them a little bit bigger. Probably not. right? So the Emacs only scales this specific number, but it doesn't scale the image. So one of the things we probably want to do, we want to open it in Theh, right? So I'm going to scale it up. Right, we can take these images and we can try to analyze them and automatically generate the cellular automaton based on them, with you know, some certain goal, for instance, with replicating the whole image from a single pixel. I don't know if that's possible. We can try to basically traverse left, right, top, bottom and see the neighboring pixels left and up, and for them create transitions that will recreate all of the pixels or something like that. I don't know, we can try. Or maybe try to come up with transitions that transition one image into another one and just actually sort of train this entire thing in all of the images. So the possibilities are limitless, right? So we just represent this in a more abstract way, and what we want to do, we want to play with this entire thing, right? We want to play with this entire thing. Does it make sense? So we spent yesterday stream sort of implementing the engine for this sort of like cellular automata, right? Because you need to write a little bit of code that can take this transition table and sort of interpret it, right? So this is what we spent yesterday's stream on. Today I want to spend on actually like finishing it off and maybe generating some cellular automatons and seeing how they will, you know, behave, right? Maybe we will find something interesting, right? Maybe we'll find something interesting. Sounds good? Sounds Gucci? Sounds Atamaguchi? Okay, so we got some subs. So we got a sub from Doorbell Prod. Thank you so much for 4 months of tier 1 subscription with the message, I'm so excited to see you, Toast. I'm so excited to see you too, Doorbell. Thank you so much for gifting money to Jeffrey Bezos. He really, really needs those monies. Alrighty. So, yeah. So as you can see, it's already deployed on the GitHub pages. It's super easy because it's a static application. You can find it in here. You can play with it if you want to. You can just make it go wild, right? And it just going wild. There is no autoplay in here. Maybe we're going to implement it at some point, right? But it does in fact look like Game of Life. Right. So there is one problem. With this kind of representation of cellular automatons, is that it is extremely wasteful, right? It is extremely wasteful because here we use, for this sort of like inner tables, we're using indices as the amount of neighbors of certain state, right? So, but here is an interesting thing. You cannot have more than 8 neighbors. So the whole amount of neighbors is straight up 8, right? So essentially, if you take a look at the square, you are at the center of the square and these are your neighbors. If you count the amount of neighbors, you will see that there is no more than 8 of them. So that means no matter what kind of states of cells you have in here, right, it doesn't really matter. Their amount will always add up to 8, right? So, for instance, let's actually call it D. We have 2 A's, we have 2 B's, we have 3 C's, and we have 1 D, right? If you sum up this thing, you would end up with 8. Right, and it doesn't really matter like what, like how many states you have. All of them are gonna, you know, sum up to 8, which means that not all of these cells in this specific table are even valid cells. Like, not all of them are even valid cells, right? So it's a huge waste of space, right? And we want to have a little bit of a better representation for this entire stuff. So because we have like this multi-dimensional sparse matrix, right? Do you guys know what is a sparse matrix? I think there is notion. I heard that notion from people who develop things like BLAS library, right? So for linear algebra and stuff like that. Right, I interacted with these people a little bit and they threw around a notion of such things as sparse matrix. Right, so and the idea of sparse matrix is that you have a huge matrix, but the majority of the elements in that matrix are filled with zeros or maybe ones, or primarily with zeros. And you have like a few like islands of some numbers here and there, but the majority of the matrix is just freaking zero. So representing this kind of matrix in sort of in two-dimensional array is a straight up waste of memory, right? So people usually don't do that. So they come up with such things as sparse matrix. So they represent basically, they only store these islands of numbers, right? And that's it. And they assume that the rest of the numbers are zeros, right? So that way you essentially cut on the amount of space, right? So that's basically what's going on here. We can do a similar thing, right? We can actually do a similar thing, right? So each individual index is basically an array of numbers, right? So essentially, let's imagine that we have 5 states, right? So that means the amount of neighbors is going to be 1, 2, 3. We already have 6 of them, right? So this is going to be 2, and this one is going to be 0. So all of them add up to 8. We can try to use this array of numbers as sort of a key. In the object, right? So maybe instead of this two-dimensional thing, we're gonna have a single object where the key is this sort of array. But as far as I know, you can't really use arrays as the keys in a JavaScript object. This is not particularly a thing that you can do, right? So, but we can be a little bit more observant in this specific case, right? So since all of the indices here are going to add up to 8, none of them ever are going to be greater than 8. They're only going to be equal to 8. And 8 is less than 10, right? So that means it is super easy to just convert all of these things into string, right? All of these things into string and just turn them and just basically join them. And this is going to be a unique ID for that specific combination of neighbors. Does that make sense? Because you would never have 4 states and the amount of neighbors of the 4th state is going to be 20. You will never have that because all of them always have to add up to 8. And 8 is less than 10, so that means it will always take up 1 digit. So you end up with a string where a single character is a single state. Right, so that means you can just like uniquely represent that specific point in that multidimensional matrix with just this string by concatenating their indices. Does it make sense? Right. And that greatly simplifies the whole thing, right? So essentially, these are the indices, and then you can say, okay, when you have 1 neighbor of that state, 2 neighbors of that state, 3 neighbors of that state, 2 neighbors of that state, and 0 neighbors of that state, right? And that state, you switch to the state 2, like this. And maybe so the rest of the things that are not set up, we can have some sort of a default key, which is going to be always 0, right? That way, we basically represent it like a matrix. It's not really a matrix, right? So when you have multiple dimensions, this is not the matrix. This is called, I think, tensor, right? I'm not a mathematician. I have no idea how it is actually called. But yeah, so basically you have this sort of like a 5-dimensional table, which is completely filled with zeros, and only at that specific point it is 2, and it tells that in this specific combination of neighbors, right, in this specific combination of neighbors, you have to switch to the state 2, right? So that's basically the idea of sort of compressing this entire thing. So I was thinking how to compress this entire representation of the cellular automaton off screen, and this is what I came up with. I think it's a pretty reasonable for JavaScript, right? So it kind of works well within JavaScript with, you know, with all of the objects and stuff like that. It's relatively easy, right? So we can try to do that. So the question is, if I have something like this, how do I join all of that into a string? I have no idea. Right, so JavaScript join array of numbers. Is that a thing you can do? How can I join an array of numbers into one concatenated, and we can't really see the rest of the message? One concatenated numbers, yes. How can I do that? Yes, somebody asked that specific question. You just join it, right? You just join it, so you can do something like that. But you have commas. Oh, this is because you have to provide this separator. So that's how you can do that. Isn't that poggers? I think that's pretty freaking poggers. You know, dynamic languages, am I right? Dynamic languages. So it would be kind of nice to maybe create some sort of a type for this kind of table, because we are programming in TypeScript, right? So we have a statically typed compiled language. We compile in a statically typed language into a dynamic one. And maybe we would like to have an interface, right? Something like, I don't know, state. So it's more of a state transition, but essentially I want to say that it's going to have basically some keys of string and convert them to a number. So I remember TypeScript. TypeScript interface key value. Yes, something like that. There was a sort of like a syntax to sort of represent the key value stuff, like indexing for indexing specific interfaces. I don't quite remember. So yeah, this one. Yeah. So essentially you can create an interface and can say, okay, so it's going to be like a string, right? So it accepts a string and it returns a number, right? Something like this. So, and then we can even say something like that. It's also going to have a field default. It's a keyword, but if I remember correctly, you can actually wrap them in parentheses and also have it as a number, right? So, and this is going to be a legit interface that you can actually use to represent things. So this is just a single state. And then maybe, right, so this is basically a single element in this specific array, right? It's this specific array. Maybe we're gonna also have a type automaton, which is basically the array of states. And we can say that the game of life specifically is automaton, right? Automaton. There we go. So after that, maybe we want to try to recompile all of that, but let's actually do the following thing where we take the TypeScript and run it in a watch mode, right? So it will constantly recompile this entire thing, right? It will constantly recompile this entire thing. As you can see, it is in the watch mode and it's completely fucking failed because, of course, I changed the signature of this entire stuff, right? I changed the signature of this entire stuff and probably have to, fix that. So here we have an array, right? Two-dimensional array. So the row that we set 1 at is at 0, 1, 2, 3, 4, 5, right? Okay, so it's 5, and the column is 0, 1, 2, 3, so it's 53. So essentially, instead of this specific element, we want to have an object, right? An object with the key 53 that switches to 1, and the default one, right? And the default one is going to be 0, right? So we say that one specific thing in here is going to be 1, and the rest of them are going to be 0. And thus we compressed this entire thing into just this. Isn't that cool? I think that's pretty cool. Look at that compression. Look at that compression. We just squeeze that motherflipper. Can you say automating the atomic tomato automation 10 times? No, I cannot say that 10 times. Because you didn't donate. Ahaha! Anyway. And primarily because I'm trying not to be a clown, I'm trying to be a software developer. Right. Okay, so I'm here to develop software. So now we need to introduce these two ones, right? We need to introduce these two ones. So this one is located at 0, 1, 2, 3, 4, 5, 6. So it's 6, 0, 1, 2, 62, not even 69. In 69, we're never going to have a 69 because it doesn't add up to 2, right? So this is a 62. And this is going to be this one. And as far as I know, this one is 53 as well, right? So it's 5, 3, so this is a 53. There we go. And the default one is going to be basically 0, right? So there we go. And we managed to compress this entire thing into just this specific table, right? So now we probably want to go through the compilation errors, right? So let's actually go through the compilation errors and actually fix them. Right, so this is going to be TSC, and I'm just going to run it. I'm just going to run it. Okay, so let's go through this entire stuff. So state, so I already have a type state and it's a number. Okay, so this entire thing is not really a state, it's a transition, right? Let's actually call it transition. So automaton, it's a transition, and transition, there we go. So I think it makes a little bit more sense now. So we have implicit this thing in here. It says something about automation implicitly. Can't be used to index type number. That is kind of weird, not going to lie. Right, okay, so I see what's going on. So essentially, here is the neighbors. What we have to do is basically join all of that stuff like so. And hopefully that will work, right? Hopefully that will work. So it seems to be working, so it's compiling, and now it actually worked. So it was relatively easy, but here's the thing. So this specific transition, right, so we can even do something like transition like so, and then just put it like that. So we may not have that specific combination in that specific transition. So if I understand correctly, in that case, it will basically set next to undefined. And because of that, we can do the following thing. If next RC turned out to be undefined, we're going to set this entire thing to transition default, right? So we're taking the default thing in here, and that's basically it. So yeah, it's actually kind of cool. So the whole thing that computes the next board is rather small. It's just a lookup in the transition table. It's a simple lookup in the transition table, and the transition table itself is also rather small, right? So this is actually kind of cool, right? This is actually super cool. I really like that. So let's see. It seems to be compiling, right? It does in fact seem to be compiling, and let's actually open that in the browser, right? Let's actually open that in the browser. So let me see. This is the what is it called? Glider, right? So this is a glider, and it seems to be working. Right, we can try to break the glider, right? We can try to break the glider by removing one of the rules, right? So here you're supposed to have 2 alive cells or 3 alive cells. We can actually say that you only can have 3 of them, right? And it's going to be a completely different game now, right? I probably don't have to recompile it because I have auto recompile. Right, so if I put the glider in here, it is not going to, yeah, it's doing something weird. It's not gliding because it's a completely different cellular automaton, right? So it's completely, yeah, it turns into something funny, haha, funny, if you know what I mean, right? So let's actually remove this kind of thing, then go to alive, like, aha, funny. Anyway, so and it in fact working, right? So would you look at that? So we can actually try to code more different cellular automata, right? So because Game of Life is not the only one, right? In fact, some time ago, I was already experimenting with cellular automata, and the project that I was working on was called, I think, Automata. Right. So basically what I did, I just like went through one of the famous cellular automata and just implemented them in C. Right, so there's a rule 110, but I don't really care about rule 110 because it's one-dimensional. Conveys Game of Life, and things like seeds, for instance. Have you guys heard about seeds cellular automaton? Or maybe about something like Brian's brain? everyone heard about, you know, Game of Life, but have you heard about seeds? The God seed, Cellular Automaton, or Brian's Brain. And Brian's Brain is actually very, very fucking cool. It's way more, it's cooler than Game of Life, right? At least the pattern that emerges out of the Brian Brain are really fucking cool. So, oh, there's also Wire World, yeah, which basically, which is really, really interesting because it's a very simple cellular automaton which implements like a semiconductor logic. But it's a convey Game of Life style cellular automaton, but it behaves like semiconductors, so you can make computers out of that. Right. So, and it's extremely fascinating. It's just like Wire World, as far as I know, it just consists of several just states, like 3 or 4 states. 4 states, right? It's literally 4 states. And you can have like logic gates in here, right? It can like conduct some stuff. It can just like do interesting shit. Holy shit, I should actually maybe spend like another sort of like a stream playing with this thing. I don't know. It's kind of cool. It's so, this kind of shit is so underrated. Why nobody's talking about this shit? Right. Why nobody's talking about this? It's just like 4 states and like a transition, and we can probably implement all of that stuff. Right? Anyway, so I'm gonna give the link to the Automata project, right? So there's also a couple of other things in here that I didn't implement, I plan to implement. Maybe I'll get back to them at some point, but yeah, so I'm gonna give the link to here, right? So, and I'm gonna also put that in the description for anyone who's interested in this kind of scheisse. Coding Trains talked about it. Interesting. So I should probably search for one of his videos where he talks about this kind of stuff. So let's try to implement seeds. As far as I know, seeds is one of the simplest one, right? Seeds is one of the simplest one. So you have 2 states. Yeah, so this is actually really cool. So it just grows like cancer, basically. Yeah. So, and I don't remember the rules. So, and the rules are basically described in with words, right? It consists of an infinite 2-dimensional grid of cells, each of which may be in one of 2 states, on or off. Each cell is considered to have 8 neighbors, Moore neighborhood. Oh, this is called Moore neighborhood. Okay, so I think I knew about that, but I forgot about it. So the thing that I usually compute is called Moore neighborhood. Alright, so I'll try to remember that. So in each time step, a cell turns on or born if it was off or dead but had exactly 2 neighbors that were on. All other cells turn off. Those in notation described in family of cellular automata containing life, blah blah blah. Okay, so let's actually try to encode the seeds and see if it will, you know, behave like seeds. So this is seeds. This is an automaton. There we go. So it has to be this thing. So if this thing was off, right? If this thing was off, but had exactly 2 alive neighbors, we have to turn it on, right? We have to turn it on. So if you have 2 alive neighbors, that means you have 6 dead neighbors, because this kind of stuff has to add up to 8. Right, and then we can say something like default, and by default it is equal to 0. Right, in case of 1, I suppose, yeah, I suppose if you were alive, you just die, essentially. You simply die. Alright, so in that case we can just say 0. And that's it. That's how we encode the seeds cellular automaton. So we're gonna basically enable it by finding where we use goal and just to replace goal with seeds. Right, so we still use goal in the name of this thing, so maybe I'm gonna actually query replace this name and get rid of the goal prefix because it's irrelevant now. Or maybe it would be even cooler to basically accept the automaton as an argument of this function. Right, so it would be even cooler. So let's call it something like automaton, and this is going to be an automaton. There we go. And in here we're going to just do automaton. Luckily we're using a proper language right, we're using the proper language, so that means we can just go to the compilation errors and easily refactor everything. Isn't that poggers? Isn't that poggers? I think it's pretty freaking poggers, mate. So what the hell is going on? So yeah, I forgot equals, of course. I forgot equals, as usual. Happens to me all the time. Okay, doesn't compile. So here we provide the two states, and what I'm going to be doing, I'm going to just providing the seeds, right? So I'm just providing the seeds, and I think that's it, right? So because I call this thing only once, so that means that should work. So interestingly, I also provide the amount of states, right? And the amount of states is really important when you're computing the neighbors, right? Because essentially, you may look at the neighbors and you may find you have neighbors only of 2 states, but you are operating in a universe that you can have 5 states. So that means you need to indicate that the rest of the states you haven't seen, you know, you have 0 of them. So because of that, you need to know how many states you have in your cellular automaton. So that's why I was also passing the states, because it's kind of a very important sort of variable. But I think we know the amount of states in the automaton, right? Because in the automaton, you have an array, and the size of the array is the amount of states you have in a cellular automaton. So basically, by passing this entire thing, you pass this thing as well. So you don't really need to pass it anymore, right? So in a place where you use that, we can just use automaton length, and that's it, right? Emacs is just being weird today. You know what I mean? So we can even, like, we pass all of the necessary information to actually, you know, look up the neighbors and stuff like that. So I think it's pretty poggers, isn't it? I think it's absolutely freaking poggers. Alright, so let's actually go in here, so we don't have to provide this thing anymore, so it's just seeds. Yeah, this is actually kind of cool. Compute next board, you provide cellular automaton, the current board, and the next board. So that's pretty cool. I like how the requirements guide the refactoring of the code. You know what I mean? Right. So you don't try to, you know, architect or design your application upfront, right? You don't try to do that. You just like look at your current requirement and you implement the minimum amount of code to fit this requirement. The requirement change and you make the minimum amount of refactoring to accommodate those changes, and the architecture evolve itself, it adapts itself to the new requirements all the time. You don't need to actually architect upfront, right? And doing that is actually virtually impossible because you may not predict the requirements upfront, right? So rather spend the minimum amount of effort to accommodate the requirements, and that's it. You spend the minimum amount of effort, so that means you made the most optimal thing, right? So, and it just like evolves, right? You just have to look for it, right? You compress these things and just, yeah. This approach takes skill and experience exactly like any good shit. If you want to have good shit, get ready to pay for it. There is no free good shit, of course. So, anyways. Okay, it seems to be compiling already, right? So let's see if the seeds actually work, right? So I'm going to refresh this entire thing. So I'm going to put the glider in here, and it should not work, right? It should not work because this is not Conway's Game of Life. And yeah, ironically, I'm not even using my local application. I'm using the deployed application, so it's a wrong thing, right? So this is the right thing, and let's try to, yeah, that looks like seed. Yeah, so it does in fact grows like a cancer. So the cool thing about the seed is just like it's when you know it when you see it, right? So it has a very characteristic sort of behavior. It just like grows like a cancer. It's just like it grows and there is like a static noise inside of it, right? So that's what's interesting about it, and it's just like, as you can see, at some point it just like consumes with a static noise. You start with like 2 things in here, and it's just like well, I mean, this one just collapsed, but usually they don't collapse, they just perpetuate indefinitely. Why are they collapsing on me today? I don't know. Have a go. Now it starts growing. It starts growing like a cancer. We don't really have like a good resolution for all that. So the cool thing in here is that we didn't really modify the logic of the engine, right? We didn't modify the logic of the engine. We just changed the transition table, right? So it's just like a different transition table and nothing else. So I wonder if I can just like increase the resolution and make it 64, for instance. Right, I think I should be able to do that. It also would be kind of cool to be able to just draw this entire thing. So right now I have to like literally click, and it's not particularly convenient. There we go. Look at that. So also off screen I made the board wrap around, right? So because I don't want to implement the infinite one, I just like made it wrap around. Right. So, and it's so cool to see like emergent behaviors out of these things. It's so freaking cool. I really like that. But then at any point you can switch the current thing from seeds to be goal, right? From seeds to be goal, and it's completely different Cellular automaton, right? So this one is going to just work fine, right? So this one is not going to grow or collapse or anything. So this is a classical game of life, just a different configuration of the transition table. So let's try to go into more complicated ones, right? So the ones that have 3 states, for instance, right? So for example, Brian's brain. So the coolest thing about Brian's brain is that it introduces the actually 3rd state. On top of dead and alive, it has a state dying, right? So essentially, if you are alive, you switch into dying, and if you dying, you switch into dead. So it adds a little bit of the time while the cell is dying. But apart from that, if I remember correctly, it acts like seeds. It's just seeds, but with the cell slowly dying. And it creates a very interesting effect. You would say like, just basically it's dying longer. But while the cell is dying, it actually blocks other cells from spawning in there. And that creates even more interesting emergent behavior, right? It's actually very, very cool. So let's try to encode this entire thing. Let me see. Let me see. So this is how the emergent behavior looks like. So yeah, it creates a lot of gliders like flying around in orthogonals and stuff like that. It's just so freaking cool. Right, so let's go ahead and try to implement this thing. So consists of finite two-dimensional grid, but unlike seeds, each cell may be in one of 3 states: on, dying, and off. Each cell is consist of okay. The cell turns on if it was off but had exactly 2 neighbors that were on. Just like birth rule in seeds, all cells that were on go into dying, which is not counted as on, right, and prevents any cell from being born in there. Okay, so let's introduce Brian's brain, automaton. There we go. So this is the automaton. So this one is 0, so that means we're gonna say that this is the dead one, right? So this is the dead one. 1 is live, and this one is going to be 2, and let's say that this one is going to be specifically dying. Implementing dying is really straightforward, right? So basically, regardless of your neighbors, you always switch to dead, right? So it's almost like programming a Turing machine, right? It's like, yeah, this table is just like a small Turing machine that reads the amount of its neighbors. The read operation is the amount of the neighbors. Based on that, it doesn't really write anything, it just switches the... Yeah, it's literally a Turing machine, holy fuck. It's actually pretty cool, I really like that. Okay, so as far as I know, if it's alive, right, so in case of the seeds, it will just straight up go to be dead, right, but here we have to actually switch to dying, right? If we're alive, we always switch to dying. If we're dying, we always switch to dead, right? And in dead, we don't really care about the dead neighbors. we become alive only when we have two alive neighbors, right? And we don't really care about the dying neighbors as well, right? And essentially we have to switch to 1. So essentially I put sort of wildcards in here, right? We don't really have such syntax in our table interpretation, but essentially what I'm trying to say in here is that we need to generate all of the possible combination of these two numbers that add up along with 2 to 8. So effectively we need to come up with all of the combination of numbers that add up to 6, 8 minus 2, right? So this one is basically going to be 0, 6, right? This one adds up to 8. So essentially when you have 0 dead neighbors, 2 alive and 6 dying, this is a valid transition to alive. So as you can see, this is sort of like a flaw in the design of this table, right? But it's only a flaw if you are manually creating them. It's not particularly convenient to create this kind of stuff manually. But again, it was not really designed to be modified manually. So I do that just to test things out, right? So because of that, I think I'm okay to do it like that for now, right? So, but generally, if I were to, you know, code this kind of stuff like manually, I would probably come up with some sort of like a wildcard syntax that allows me to match certain things. Right, so these are possible combinations in which we have to switch to 1. So as you can see, adding new states adds, you know, quite a few, how to say that, like combinatorial complexity, right? So because you have to take into account all of these combinations and stuff like that. So by default, we don't really care about the rest of them, so we always stay at the det. And I suppose this is the Brian's brain encoding, right? Brian's brain encoding of the Cellular automaton. Right, so let's actually see if we didn't do any fucky-wacky and potentially an oopsie-doopsies. Potentially oopsie-doopsies. So here's an interesting thing. So we have 3 states in here, right? But our UI editor supports only 2 of them, right? The dead and alive. We cannot create dying one, right? Because it just literally, we literally hard-coded the amount of things in here. But as we start interpreting things, I think it will still draw it, right? Because we have a so-called caller table. Yeah, caller table. And essentially we can display up to 4 different states, right? So if you have like 3 states, I think it's going to be rendered with green. So the dying cell is going to be basically green. All right, so did I actually switch to, yeah, I didn't switch to Brian's brain, so let's actually do that. We didn't have any errors, right? Okay, so let's actually put some stuff in here. And let's try to compute the next cell. And as you can see, everything I put in here is actually switched to dying. So it worked, right? So it means, yeah, we can continue. And it collapsed. So maybe we need to have more of these things, right? So let's actually try to do more of this stuff and see how it's gonna go. Yeah, there we go. Now we see the patterns. Now we see this entire thing growing. That's actually so cool. And it's working, right? It works exactly as you would expect. So this is a Brian's brain. Yeah, it creates like a lot of orthogonal gliders, right? So it's sort of like an emergent behavior of the Brian, and it creates this kind of thing. That's actually so cool. Ah, I love it. Yeah, it's really trippy. And what we're doing in here, we're just modifying the transition tables, right? We're not really modifying the code, the logic per se, right? So all of that is transition tables. So that means you can kind of generate this kind of transition tables, maybe. I don't freaking know. Look at that! Look at that spaceship. It creates so many spaceship. Yeah. This is so fun. Yo, and they're gonna actually collide again because it's wrapping around. So one of the things we probably need to have, right? We need to have some sort of autoplay, right? Autoplay. Another thing, basically drawing the cells, right? Because right now I cannot just hold down and draw, right? I have to click each individual thing. It's not particularly convenient. Another thing I would like to have is probably, you know, automatically give me the populate the radio buttons, right? So because radio buttons are hard-coded, so what we can do, we can basically have a global variable, like the current automaton. It's called BB. And since we know the size of the current automaton, we can populate the radio buttons. So depending on the current automaton, you can basically like set like any sort of state, right? So any sort of state. So this will be actually kind of nice. So auto populate radio buttons based on the current automaton. How do you spell populate? I don't really know. So I'm gonna ask Google, how do you say populate? I think I spelled it correctly, maybe. So it's actually single L. I'm sorry, I don't speak English. Right, autopopulate radio buttons. So this is basically from the usability point of view, right? Something that I would like to have. Interestingly enough, right now we just have a global table of colors, right? Global table of colors. And so the index of each individual element corresponds to the state associated with that specific color, right? What if we have more than 4 states, right? How many states do we have to accommodate in here? I don't think it's a particularly great idea to do it like that. I think what would be better is to maybe, for a specific transition, to have a color associated with it, right? Just get the color from here, right? So here we have a default transition, and on top of that we also have a color associated with that specific state in that specific cellular automaton. I think that's a good idea, actually. So, and get rid of this global table. So basically each individual transition table also encodes how to color itself. And you know what? It's going to be extremely useful when we're going to start generating the cellular automatons based on the images, right? Because, yeah, right, because the image also... so what we're going to do, we're going to iterate through all of the pixels of the image, and we collect the unique pixels, and the collection of unique pixels is going to be the amount of states of that specific cellular automaton, right? I think that makes sense, right? Does it make sense? I think it does in fact make sense. Right, so yeah, let's actually quickly do that, I suppose, right? So if I just add color in here and just comment out this color in here, right? So it will create a lot of compilation errors that I'm going to be forced to fix. Where cute people? I can show you cute people. So people are asking where is cute people. So this is what we have in here. Yeah, these are cute people. Are they cute? So I probably need to actually, so here's the license. So CC BY, you may use this graphics in person, commercial projects, credit. Yeah, so that's the creator of this is the artist, right? Created by a human, not an artificial intelligence. So I actually downloaded it on Open Game Art. Right, so it's actually pretty cool, pretty cute icons. So I specifically chose them because they're very small and they have a limited amount of colors. So they're kind of perfect for cellular automatons. Very cute indeed. So cute people, I think. Yeah, there we go. So it's this one. I can copy paste the link in here. So if you're maybe interested in other works of this author, you can check them out. So they created a lot of cool stuff. Look at that. I wonder if the AI is going to ruin this kind of website, because people may start posting shit generated by AI or something. This is actually super cool. Look at that. I really like that. So so I'm going to, did I put that in the description? So I think I'm definitely need to put that in the description, right? Because I want to credit this person. Cute people. Oh yeah, there we go. So these are the cute people we have. Right, I was going through the compilation errors, I suppose. So color string is not property color of string is not assignable to string. This is really strange. I wonder why. Property color of type string is not assignable to string index type number. Ah, I see. I freaking see what's going on. These two things conflict with each other. Fuck. You know what? I think I can remove that. Right, because interface sort of like defines like a subset of the fields, right? Required like a minimum subset of the fields. And color and default are in fact the minimum, the bare minimum of the fields that you have to have in the transition, right? Because you may have like a default which doesn't really, like it ignores all the neighbors, right? But it has to have the default and the color, right? So if we're gonna have more on top of that, that's like, you know, your choice, right? So that's the transitions you defined and stuff like that. So yeah, I guess that's good. That's good. Okay, that makes sense. It would be kind of cool to encode some sort of like invariants that we put into the keys in here. Yeah, it would be kind of cool to somehow, on the level of a type system, to encode that the string consists of digits and the digits add up to 8. So, but I don't think the TypeScript type system is so powerful so that we're able to encode this kind of stuff. Maybe in something like Jai, it will be possible to actually write it like that. So it is possible to write it like that. I wonder. So it basically can have so JavaScript code that is executed at the compile time. Also sort of Jai. Yeah, in Jai you can just like literally run any code at compile time. But there is also a lot of runtime when we're going to be training our automata. So these keys are going to be runtime values, so that means they has to be checked at runtime. So we'll see. I don't think it needs to be this strict right now. Okay, so let's actually define the colors. So this is the color, and let me just grab 2020. So all of the dead colors are going to be the background, right? So they're going to be 2020. So all of the alive are going to be reddish, so to speak. Right, they're going to be reddish. So game of life, the same. The dead is going to be that. The alive is going to be that. And the Brian's brain is really interesting, right? Because it has 3 states. So if 50. So this is alive. And this one has to be green, so I'm going to put FF in here. Okay, so I don't think we need this global table anymore, right? So let's see what other places we have to modify. I think I know why there is a watch mode for TypeScript compiler. So 69 number is not assignable to type transition. Really? I thought the interface is sort of like a superset, isn't it? Can I say something like this? I don't freaking know. Right. Is there any way to say that I can have more types in here, or is that not possible to say at all? It's not possible to say at all. So I suppose we have to do some stupid shit like key, string, string or number. That is dumb. So I could have just programmed directly in JavaScript. What's the point of TypeScript at this point anymore? I don't fucking know. Anyway, so what do we have in here? Is not assignable to number. And now you're starting to have this kind of shit, right? So because you didn't have a guarantee that this kind of stuff is gonna be a goddamn number. A goddamn number. So essentially, one of the way we can fix this entire stuff, right? I suppose one of the way we can fix this entire stuff is maybe to say that transition, right? Transition is, you know, it's something like it has these separate tables, so to speak, right? Ooh, so basically a separate thing in here, but I'm not sure how to call this entire thing. So this is a transition, right? So I would like to call this a state, right? So this is a state and it has a certain color and certain default, and this is transitions, right? These are the transitions, and that would make more sense in my opinion, right? But unfortunately I already called state just a number, so but maybe I should call it a cell, right? I should have called this entire thing a cell, right? I think that makes a little bit more sense. Okay, let's actually go to the compilation errors. Alrighty, so what do we have in here? So I have to actually use the cell in here, right? So this one, number is not assignable to state. That means I have to recompile it one more time. Okay, what else do we have? So this is the transitions. Did you mean CSS transitions? No, I didn't mean that. So I meant states. Okay, so let's go to the rest of the compilation errors. Compilation errors. Compilation errors. So that means I have to do transition in here, right? Transition. So, and I think it looks like a right thing to do, right? It just like separates what you can have in here. Transitions. This is gonna be that. I forgot a comma in here. So the entire thing, the entire representation is a little bit growing, but it's still smaller than if we used something like a straight up multi-dimensional array. Right? In case of multi-dimensional array, this kind of stuff could have been enormous, freaking enormous. This is still smaller than that. So let's quickly do that, and yeah, this one is a big one. So this is transitions, and let's put it like this. There we go. So transitions like this. So I suppose I forgot to put a comma in here. Let's take a look at the compilation errors. Okay, so now we're talking. So is not assignable to a type string. Yeah, that's true, because I put string in here instead of a number. Thank you, TypeScript. Yeah. TypeScript is catching an errors that I wouldn't even have if I didn't use TypeScript, right? So, okay, so this one, we probably want to call it a state, and within a state, we use transitions, right? So this is transitions, we do that. Right, and here we can do state default. Maybe yeah, so that should actually work. Okay, so state colors. All right, so this is where we need the colors of this entire stuff. But we have it in the table, in the transition table. So that means we need to accept automaton as an argument here as well. Look at that. Right, automaton. So because this is where we have all of that, right? So it's an automaton. We take the state and then we take the colors. So that's what we have to do in here. Right. Did you make dying, dead, alive enums? No, I didn't make them because we don't need them, because of how we represent things. They're not needed at all. So, right, so we have a current automaton. So maybe I need to put it in here, right? So, because now, when we're rendering, we do current automaton. So this is the current automaton. Then we do current automaton, not board automaton, on the current board to compute the next board. Then we swap them around, and then we're rendering the current automaton. Yeah, there we go. So it's actually working out quite well. I really like this. I really like this. So we're slowly factoring out everything. Big ass refactoring, exactly. Big ass. All right. So let me see. You know what would be even cool? You know what would be even cool? Right. So in the where is my page? Here in the page we have like a radio button, right? So it's just like a dead, alive, and all of that is hard-coded, of course. But what I want you to do is to make it basically populate depending on the current automaton. Right, and with each individual state we have a caller associated with it. So what if we get rid of these names and literally put a square with that specific caller in there? So it could be viewed as a palette. Yeah, so essentially a specific automaton has a palette associated with it. Right, you select a palette and then you can put that palette in here. Right. And then maybe you can have like a combo box where you can switch between cellular automaton, and by switching it also switches the palette because it's associated with the current automaton. And all of that is encoded in just a transition table. Right, it's actually kind of cool, right? That the transition table, like plus additional information, just encodes everything. Right. Or you could add name next to caller. Here's the thing. I plan to generate those cellular automata based on pictures, and that means I don't have a human readable names associated with any of the states because they're just pixels or colors, right? Because of that, the names are just like really meaningless in that sense. Right, they're kind of meaningless. So maybe I don't want to have like associated names actually, right? Maybe I only want to have a colors because that's the direction I'm moving towards. But we'll see. All right, so yeah, that's pretty cool. So right now we have a Brian's brain. So this is a Brian's brain and stuff like that. So it would be kind of cool to rat hole on all of these to-dos, but I feel like I'm already spending too much time on the UI part of things. I would like to do some actual computer science, if you know what I mean. I'd like to do some actual computer science and actually move on trying to read the image, right? So let me actually open it in here. Right. Can I increase this entire thing? I think I did a fucky wacky and potentially reduce that. Yeah. Right. So I want to basically open up that, read the pixels, and try to transform all of that into the transition table and stuff like that, and see what kind of cellular automatons we can make out of these images. Right, so but before I do that, I want to make a small break because I've been slapping the code and doing big ass refactoring for an entire hour without any tea, because I pour myself a cup of water before the stream, right? So it was not a tea. So, right, and I really need a little bit of a tea. So let's make a small break, and after the break, we're gonna continue slapping the code.